in the past few lectures, we covered quite a few graphic models to the point that we ran into a model that is not able to have efficient inference algorithm. Therefore, we start to enter the regime of approximate inference. So today I'm going to dive deeper into the approximate inference technology, and also to, if time allows, present a bigger theoretical picture about what's going on. So, do I hear myself over there?
Yeah, I'm watching.
Okay. All right. So this is basically a recap of what we know as an inference problem. It's about computing the conditional probability of some subset of random variables given another set, or sometimes it's about computing say likelihood of the data and so forth. And the method we ran into so far, okay, includes like the brute force variable elimination, which you already had a lecture before. And then, we also mentioned that the variable elimination algorithm is very similar to a message passing algorithm, which I'm going to briefly review today. And typically, you are going to, turn the global, marginalization problem into some local operations, which allow you to step by step eliminate variables of no interest and focus on the queries that you worry about. Right. So here is hopefully a conceptual picture about how elimination ties to message passing. So here we begin with a joint expression of the joint probability in terms of a product of factors, and then to do say marginalization of random variables really amounts to eliminating term in this multiplication. The term corresponds to a local conditional distribution, or in the Markov random field case, potential functions, of a subset of random variables. And very often when you eliminate a few terms, you create also some new terms. And this equation we saw before is giving you basically the tracking of all the intermediate terms we created. And then we recognize that they correspond to cliques of random variables, that can be captured by this graph on the right. And then, eliminating, all these cliques one by one actually correspond to doing a message passing, on this tree of cliques, such as this, okay? And in fact, the message passing can occur on the tree in both directions, so that, every edge corresponds to a message going forward and backward. At the end of the day, you can use, the messages to compute statistics of interest. One of the utility of this message passing protocol is to help us figuring out the complexity of the inference, because every of this clique, such as this one represents a local operation that has to be computed exactly. Therefore, the size of the clique corresponds to basically the bottleneck of the inference algorithm, and we call them the tree widths. Right? So these are some reviews. And also, we mentioned that if you find a good way of elimination, then that sometimes can reduce the size of the maximum elimination clique. But if you do bad ordering, you can get into sometimes a very big clique. Do you still remember what could be such a bad elimination order in one of the typical graphs? Remember that the start graph, right? If you eliminate from the center, you are going to connect all the rest of the nodes into a single clique. That makes a very big clique. But if you eliminate from the peripheral, from the edge, or from the leaf, then you could actually each time result in a new clique that is only having two nodes. And once you have the clique tree, there is an algorithm that we actually talked about, which is called sum product. Right? Given that the whole graphic model is defined in this way, you can always define, a generic form of the message like this. Here we have a message, say, coming from T to S. Then this message can be computed by the factors on T, okay, which is this one, and all the other factors that is containing P, xt, which are all of these, and also all the messages coming into T, okay, from this edge. Okay, so and then after it's computed, it goes out to S. Yeah, so that's kind of a generic form of the message passing algorithm, which is actually pretty simple and easy to implement. And we have some nice theoretical properties, but let's see a message passing protocol, how it runs. Right? Suppose we have a graph like this. Then what you do is to pick maybe a particular node, say X, as the hinge point, and then you compute the message along the edge like this, and the equation of computing these messages is given in the previous slides already using this generic function. And once you do that, once you reach that endpoint, you basically go to another direction, and every node will be able to receive messages from all the neighbors. And at the end of the day, once every edge has the message passed back and forth, there is a convergence point that leads you to the final form of the messages. And then you can use them to compute all the statistics. And just to, again, recap how this translates to some operations on our known models, let's talk about the HMM, for example. A HMM is a tree, right? And on the tree, we can define basically all the cliques. And here I have two types of cliques. One is the original clique defined on the edge, and then the square cliques are the intersection of the two cliques. And once we have this, we can write down very generic message passing algorithm. For example, if we talk about a belief on this, you can basically collect a message from here, and then goes to there, right? And this is giving you a rightward message passing protocol. And the equation can be basically computed as this. Okay, you can see that it contains a message from this one, and then multiplied into two messages coming from a bottom and from the right, and then it gets the message out. So this is just a realization of the generic message passing algorithm on this particular graph, which is corresponding to HMM. But if you look at the structure of this definition of the message, it's actually the same as what we originally presented as the forward algorithm, okay, where the message Y is basically recursively defined by continuously recursively computing based on the previous version of the mu message. By the way, what is the definition of the mu message? If you remember, what is the statistical meaning of that mu message? You don't remember already, right? It's basically the conditional probability of xt plus 1 given what? Y1 to t, right? And you can basically go this all the way down to the next one, xt plus 2 given y1 to t plus 1. And the dependency between, the relationship between these two terms actually is captured by this forward passing algorithm. Okay, and then leftward pass is in fact the same, in terms of using the message passing algorithm. You get a message from here, and then you go there, and you can again multiply all of them together, just mechanically. And if you just bring back the exact definition of this term, and this term, and this term, you actually get the backward passing algorithm. So message passing algorithm, on tree is a very universal algorithm that leads to in fact, the common filter algorithm we talked about last time on stasis model is also an instance of this. Now let's move on. So all these are basically exact algorithms which gives you exact answer to the query in terms of conditional probability of say p of x t plus 1 given other things and so forth. And why it is correct? Well, I'm not going to give you a proof, but you can actually show to yourself that the very way we define this message passing based on the elimination algorithm is already giving you basically a proof which says that it is the right way to do variable elimination and gets you to a marginal distribution of a subset of random variables given evidences. And there are some interesting properties as well to a message passing algorithm. In fact, here I want to raise caution already. There is a theorem which I'm not going to prove, but you should remember. It says that the message passing algorithm guarantees to obtain all the marginals only on a tree. Okay, and here I make a very strong assumption already. The graph that I'm running the message passing algorithm is a tree graph. So anything special about the tree, if you can remind me? What's so special about the tree versus another graph?
There's only one path to not two.
Precisely. Thank you. I bet you have the same answer, right? Yeah. So there is only one path that you can establish from any pair of nodes, and that's very important because it's kind of implicit tells you that once you run the message passing algorithm, there's only one way of getting the other message. You actually have the uniqueness. Okay. And the uniqueness is almost like a necessary condition for being correct. Otherwise, if you have the same message passed from one thing to the other through two passes, then you may have two different answers. Then, of course, you need to run into whether which one is right or which is wrong problem, right? And also, in fact, the correctness can also be kind of implied from the following properties of the message passing protocol. There is a very important property that can be established from the message passing protocol, which is this local consistency. Because every time we pass a message, which is either a singleton message. Remember that we have in a generic a clique tree fashion where you have say this is a clique and this is another clique and this is the intersection of the clique SS, right? And in the simpler case, you may say that here I have x1 and 2 and x2 and 3. These are two nodes, and then in the middle you have x2, right? So you can define basically a term, a message, or a potential function on this x1 and x2 and x2 and x2 and 3. Once you do message passing, there is a very important property that you can prove by yourself using the message passing protocol, which is known as local consistency. It says that once you finish the passing, every this is a proper marginal distribution of the nodes inside the set S, meaning that they sum to 1. And in this case, that means okay, so this is first of all giving you what it is the correctness of the proper marginal, that they should sum to 1 as a distribution. And then if you have two marginals, say x what do you mean they are consistent? Consistent means that they are coming from the same distribution. It means that if you do this and the sum over x2, it should lead to margin of this, right? So basically, if you have a node x1, x2, and x3, and if you have a distribution on these two and distribution on this one only, then the marginal of the joint of a pair of nodes leads to the marginal the marginal of this node that is left out. And if you have a tree, you can imagine that you have a tree goes to, and then you can use basically the local consistency to establish global consistency. Basic means that if you have something that is a correct marginal in here and a correct marginal in here, then you can further prove basically the correct marginal can be established on every node in the tree, because there's only one path that you can pass the message. Therefore, every node and every edge gets a single convergent point of the pairwise potentials or singleton potentials. And then the local consistency can be propagated to everywhere inside the graph. Right? So that's basically saying that the local consistency can guarantee global consistency on the tree. Now, a problem can arise when you have a graphic model that is not a tree, say this one. This is not my, I have okay, this is not the latest slides that I have. I meant to have a new slide in here, but it's not there. Let me do one actually, maybe let me do a little bit more work on that. So I have this one, okay, and here how message passing can take place. Let's say I worry about A only, right? So this is one way of getting the message. Therefore, my phi of A equals to what? Okay, or my P of A, let's say, should be a phi of A times a message B to A times a message C to A, right? Okay, and then I should do, and also of course there are, yeah, that's fine. And then what? I'm going to now copy the A here. And what is this message B to A correspond to? It should have a B, and then MD to B, right? And in here, I should have a what? C, and then what? Actually, there isn't anything, because here I don't have message coming into C anymore. Therefore, that's it, right? There isn't a message from D to C, because that's not the way I pass message, right? I can only basically do one more in here. This one gets what? D to B. It becomes B of and so forth, right? And then, I'm not going to write down the whole details, but I just suggest a different color. There is another way to pass message, which is doing this, okay? And I suggest you to, I'm going to actually also post that, but I suggest you to run the same message passing algorithm and just basically compute how the marginal of A look like. I bet you will get a different answer. Okay, that's actually because you have two ways of passing the messages. And in another way here, if you want to compute, for example, click tree, using this then suddenly you have this C random variable occurred in two sides of the clique. Okay. And that's becoming a little bit tricky because here, originally we say local consistency, translating to local consistency, you usually are passing the intersecting consistency along the way and gets all over. But right now, the C is basically stayed here and here. They have no way to get exchanged in the middle. There is no way to shake hands between the two C's. Therefore, you don't have a mechanism to ensure their consistency. Okay, so that's just some high-level stories to tell you that message passing on tree algorithm is not going to give you a correct answer necessarily, and what you need to do is to basically either turn the message passing into a tree kind of writing algorithm. For example, how to turn this graphic model into a tree. You need to basically define bigger nodes, right? So what's the tree width of this? Remember, last time we did a little bit on the elimination clique exercise on this graph. What is the size of the biggest clique in elimination? It's the entire slice, right? Eventually, you are going to get every node in a particular slide connected after you eliminate in whatever order. And that's actually the tree width, okay, the clique size of the elimination clique. So what's actually happening is that you could turn this graphic model into a graphic model like this, which is a tree. But these nodes are the so-called super nodes, which contain basically all the nodes of a particular slide. And they could be hundreds of nodes. Okay, therefore, even you can run a message passing algorithm on the tree, but this tree has too big tree width. Therefore, it's still unfoldable. So that leads to approximate inference. And we saw an example last time. I'm going to make connection later this class. But let's see another heuristic people use to handle approximate inference, in the non-tree graphic models I just mentioned. Okay, sorry, I somehow lost. Okay, maybe this is fine. I still want to add a slide. Just give me a second. Maybe I can do it here. We are going to talk about today an approach known as Loopy belief propagation. And last time we actually, let's see, do I have? Okay, I will do it later. So let's look at the algorithm first. Okay, this algorithm is kind of interesting. So we know this algorithm already, which is known as message passing. And another name for this algorithm is also called belief propagation. Basically, you are going to recursively, iteratively, run this message, on all the, edges on a tree graph. And at the end of the day, when you converge, you can actually use the messages to compute, all the marginals of, subset of random variables. Okay. Now, if we have a graph like this, which is not a tree, we call them loopy graph. Guess what you should do to solve the problem? Some decades ago, people were just maybe either creative or just being careful. What they did is that, in this message passing algorithm, I didn't really, know the theory behind it, and also, I'm not really told to only run this algorithm on a tree all these tree stories was actually discovered, alongside the practice by theoreticians, but practitioners very often don't care. They say there is nothing preventing me running this algorithm as it is on any graph. Right? I'm going to basically just run message passing on it, regardless whether there is a graph, there is a loop or not, on the graph. Okay, so then people just keep running. Of course, in here, there isn't, a criterion that you can just, have a directionality that you pass the message from the leaf to the node to the root of the tree and then pass back. Just in 2 run, you are going to converge. In here, because it's loopy, therefore, your root also become the leaf. Then you can go out of the root and go down to the bottom. Therefore, you can actually pass the message on and on. And people just do that. And then after they do it, they discover 2 phenomena. Either the algorithm converge, okay, and when they converge, they discover that the solution was actually pretty good. How they verify solution? Well, you could just do brute force marginalization of every random variable in the graph, right? Just by sum over all the things, without any smart algorithm. You just basically deal with the tree width and compute it. Sometimes if the graph is like 10 or 20 nodes, the complexity is affordable. Therefore, you can get the ground truth. And you compare the ground truth with the message passing results like this, and they found that they are good. And sometimes the algorithm fail to converge. They just oscillate, between multiple answers of the B, and then people just give up. So that's a observation people find. So this algorithm was given a name called Loopy Bethe propagation. It sounds like a legitimate name that is working, but it's in fact just a hack. Okay, you just run a message passing algorithm on the loopy graph, regardless of it is guaranteed to converge, guaranteed to be correct or not. And Kevin Murphy was once my office mate. He was the first person taking a bunch of graphic models and ran this loopy belief and discovered what I just described. Some converge to a good answer, some never converge, and he was trying to give some theoretical insight into it without being too successful in this first paper. But that paper was very, very influential because it inspired some theory-savvy people to take this problem more seriously. And at the end of the day, there are some good results out of it, as I'm going to show in a second. So this is basically what's going on, right? So you basically, on every edge, pass the algorithm, pass the message, as I defined earlier, using these two criteria, two formulas. And this is another way to describe this algorithm, right? You basically are classifying, the algorithms, the messages into 2 classes. One is, coming into a node, and the other is coming out of the factor. Basically, you are going to, define factors, which are, the potential functions on the graphical model, and also the nodes explicitly into 2 partite, and then, the messages can be defined, from A to I, which is a factor to a random variable, or from a random variable to a factor. And that's basically the definition of the messages. And once your messages are all converging, you can compute the singleton marginal and the cluster marginal using, again, this formula. The formula is generically taking the form as a product of either messages or factors. Okay? And when you combine them together, you actually get a more global definition of the message passing. So what's going on here? That's basically something that I want to spend some time to talk about today. So going back to so maybe just to remind people. So the goal of inference is to get answers to P of X, say alpha, of any alpha, which is a subset of random variables. That's the goal of inference. So in here, we basically developed a message passing algorithm using all these equations on a loopy graph. And once they converge, we're going to use this equation or this equation to compute the P of alpha. Okay? And why this is approximate inference? Because we knew that on a non-tree graph, passing messages is not guaranteed to converge, and people empirically also observe that already. Therefore, the results must be an approximation. So now let's see what's happening, what has been approximated. That's actually something that is very interesting. What is being approximated, and how good is the approximation? Okay. So remember, in the previous lecture, we already touched upon the idea about approximation a little bit, right? We have a target distribution, say P of x, and we know P of x is a factor distribution, and we want to do inference on that P of x alpha, but it's hard. And then what we want to try alternatively is to introduce a new approximation Q. Okay, that is maybe a little bit easier for us to do marginalization. So why this is hard? Because this requires you to do marginalization of x minus alpha over the original distribution, and the distribution is say difficult. Okay, and then we say we want to define a distribution Q of x, so that P of x alpha can be approximated by a marginalization of x alpha over Q of x. Right, and let's forget about what Q looks like for now. Just imagine such an approximation exists. Then to measure the quality of approximation, we introduce something called a KL divergence, okay, which eventually leads to a term which is known as the free energy, right? And remember, we also set something like lower bound of the likelihood. Okay, they are the same thing. They are the negative of the free energy, as we discussed in last lecture. So this free energy is a surrogate, basically, of an objective that we can optimize to find a Q that is close to P. Now, if we remember what is happening in the topic model lecture last time, I mentioned a technique known as the mean field approximation. Right. What is mean field approximation, if you remember? It's about defining the Q to be directly a product of some little q's, each defined over, say, x of alpha. Right? And if you can, of course, they need to have some additional parameterization, say phi and so forth. That's fine. Suppose that we get a convergence of this. Then what is how we solve this inference problem? This inference problem, P of x alpha, can be directly written as Q of x alpha, directly. And that basically solves your entire marginalization problem. You don't have to sum over a huge distribution over other random variables. You don't need to do all these integration summations in the topic model cases over all words and all topics and all topic-specific word frequencies and so forth, and get a direct marginal of, say, a word probability. Right? In this case, likewise, if you define the mean field to be of not granularity of your query, you can directly get it. And the way to get all this optimum Q alpha is to minimize the KL divergence, which we see an example last time. So today we are going to see a different approach, okay, to solve this problem, which is not using the Q technique explicitly. So here is how we begin the problem. Let's start from a tree model, and let's look at this particular definition of the free energy and see how they appear on this graph. First, I want to establish a fact, which is very important in terms of getting the computation more tractable. So when you see a graph like this, let's say 1 all the way to x8, how does the joint distribution look like in terms of a function of our local marginals? By the way, here, what are the local marginals we care about? We care about the p of x, I, and j of any ij that is adjacent, right? And also p of every xi. So between this and this, what is a relationship on the tree? Okay, so let me write down a few things. So this one equals to, let's start from here. Somehow you can write down p of x7 and x8, right? And then you can also write down p of, say, x6 given x7, right? And then p of x5 given x6, and p of x4 given x5, and all the way to p of x4 given x1, right? So basically I'm going through this round. So this is just a chain rule of the distribution, right? And then if I do a little bit more, you could also realize that here I have x7 and x8, and here I could express this as x6 and x7 divided by, right? And I also could write down p of x5 and x6 divided by p of x6, right? Mm-hmm.
So this is not a direct graph, right?
It's not. I don't even use a graph. I can just use directly the chain rule of distributions and the Markov-Blanket property. Okay. Yeah. In fact, here x5 given every x6 and x7 and x8 everything, but yeah. Okay. So what I meant to get to is that at the end of the day, you can write down the joint distribution as a product of p of x pair. Give me a second. Let me finish that. Divided by here xi. Okay, and in fact, if I'm a little bit more careful, if the I is, you probably already noticed that in my denominator, this x8 and x4 never appeared, right? So therefore, here, if I'm just writing down a generic expression of a product, this I, if it runs over everything, I need to have something else, which is called bi minus 1. B is the degree of every node in the graph. So all the nodes except x4 and x8 have a degree of 2. When they minus 1, they give you 1. But for these two nodes, because their degree is 1, when minus 1, then the power is 0, therefore they vanish. Okay, so that's basically a very useful way of defining joint distribution, okay, on a tree, which is the product of pairwise marginals divided by the product of singleton marginals raised to the power of degree minus 1. That's the equation I want to use. Okay. Now, why do we write that is very interesting, right? So, okay, so we get here already. This is what we get from here. Okay, the joint of the distribution on a tree is equal to this, product of a pairwise potential, pairwise marginal, and also the singleton marginal in this way. And then I can write down what is known as the entropy function of the distribution. Okay, and you know the definition of the entropy, right? It's minus P times log P, right? So you plug this in, and you are going to get this definition. And what is the free energy? If you go back, the definition of free energy, I just want to copy here, equals to minus entropy minus expectation of every factor. Okay, that's basically coming from here. Okay, under a Q, right? Okay, so then you just now use this equation to plug in the free energy. You get basically this minus sign cancelled, and this one also negated. So that's basically this one, and you also get this one because it is to account for the subtraction of the expected factors. Okay, so at the end of the day, you get basically expression of this pairwise free energy minus a bunch of singleton free energies. Okay, then okay, that's basically called a tree free energy. Are you with me? We just introduced a definition called free energy, and we write it on tree already. Now, we have a new graph, which is a loopy graph. And how can we define a free energy on that? Well, this distribution becomes a little bit more mysterious, right? So it's symbolically still written as a P of x1 to x8. But this distribution no longer equals to the product of B of alpha and divided by the product of bi and minus to the power of degree minus 1. It's no longer equal to that. Agree? You can just prove by just writing down the whole thing and see how it looks like. It doesn't agree with this equation. Okay, and but we can still define free energy. Okay, exactly using the formula as before. Basically it's the first part is the expected log ratio of the marginal divided by the factor, and here is 1 minus d degree times this singleton entropy function. Okay, and there's a name for this definition. It's called the Bethe free energy. Okay, this is a name after a physicist called Hans Bethe. Okay, so why this is interesting? Because this Bethe free energy can be written down in a very explicit form like this, and it is not the true free energy of this loopy belief dispute, the loopy graph, but we can use this as a surrogate of the true free energy. Okay. So this is just by choice. I decided to approximate this true free energy, which actually should equal to h of x times minus h of x minus expectation of all the factors. This is rather hard to compute if we have a loopy graph, because we know that computing the entropy requires you to sum over random variables, and computing the expectation also requires to sum over random variables. And when the graph is not loopy, sum over, which is an inference problem, become intractable. So here we don't do this. Instead, we do this. Okay, and we basically treat this b and this b alpha and bi as unknown random variables. We basically say that if they are known, we can define this free energy. Okay. And that basically leads to a objective. How about we are going to solve this B of x alpha and B of xi directly? Okay, I solve these queries directly by minimizing the free energy of this. Okay, so now if you recall the mean field story, over there we say we're going to solve a Q by minimizing the KL divergence between Q and P. In here, the slide story is a little different. I'm going to directly solve all the pairwise marginals and the singleton marginals by minimizing what is called the best free energy. And why it makes sense? Because we kind of believe the best free energy look like original free energy, except that originally we use a tree graph, and here the true graph is not a tree graph. But hopefully they are close to each other. Right. So that's basically how it looks like. Remember, this best free energy can be defined on any graphical model. Okay. And you basically just introduce all the pairwise terms and all the singleton terms, and you weight the singleton terms with their degree. And then, what amounts to the solution then? You are going to now, minimize the free energy and or the best free energy. Okay? And the best free energy is a function of what? Right? A function of this. And are there any properties you want to make sure to happen on the marginals, singleton marginals, and pairwise marginals? Well, they want to be marginal. Therefore, you should make sure that they normalize. Right? And what else you want to keep as a property? Local consistency. Right? Because we have this tree idea that at least allow the pairwise potentials to be connected in a certain way. So how about this one? Okay. So basically, I handcrafted a optimization problem that leads to the solution of my marginal queries, and I use a loss function which is called the best free energy, that is correct when the graph is a tree and incorrect when the graph is on the tree. And I'm going to basically directly solve the free energy minimization problem, and this can be done by a grand Lagrangian. I basically introduce the objective, I have the normalization constraint, and I have all the local consistency constraint. And then it amounts to just solve this grand Lagrangian, by taking derivatives of the objective with respect to all the free parameters. In this case, our unknown singleton and cluster marginals. And then you could write down, in fact, explicitly the form of this. Okay. And then you will do some reparameterization. You can basically call the lambda, which is often defined. Remember, there are local consistency constraints, right? Usually, it's between a cluster and a node. You can call this this lambda to be a message, and just rewrite it in a different notation. Then you will find that the solution to the constraint optimization problem I just mentioned takes the same form as our message passing protocol on the Loopy graph. Okay. So this is kind of magical. It was never realized that this ad hoc message passing equation that we just borrowed from a tree graph and ran it anyway on Loopy graph correspond to a solution to the constraint optimization problem using best free energy. So there was a famous paper, maybe around the year I entered grad school, by a bunch of researchers who had a physics background. They literally derived this. Okay, they know what is best free energy in the physics literature, and they actually were able to make for the first time a connection between a optimization problem and this message passing problem. Okay, so I'm not going to say too much. I'm going to move on. But here's the summary. Now you see two inference algorithms already, which are approximate. One is called the mean field, where we basically use a Q to approximate B, and through a KL minimization approach, right? And this is a mean field. And in the Loopy BP, we directly basically focus on the B of alpha and B of I, and we basically are using a best free energy to approximate the true free energy, and we're going to minimize that and make a B of alpha and I of alpha to be the arc mean of the base free energy. So anything in common in these two techniques? The commonality is that somehow I turned the inference problem into now a optimization problem. Okay, and I have different tricks of determining what to be optimized and what is the free knobs in this optimization formulation. And then at the end of the day, I either directly get my query or I indirectly get my query as a simpler distribution that is easier to manipulate, and then I solve the inference problem. So it's kind of a detour toward the inference problem using some other approach. So with that, I'm going to immediately start the next lecture so that you see what is the bigger context of what we have done so far. So I'm going to talk a little bit about the theory of variational inference in the form of convex optimization. And I'm going to establish basically some concepts that gives you a more unified viewpoint, based on the variational principle and how the Loopy BP and the mean field are related. In fact, they are just two ways of approximating the same optimization problem as we are going to talk about. Before I go forward, let me make a small poll here. Any one of you have taken a convex optimization class in our department? Okay, that's great. So you know conjugate dualities and stuff like that, right? So I'm going to use that technique today. And I bet you already know the word variational methods. Do you? Great. So variational methods is basically just a fancier way of naming the optimization-based formula. In fact, many of the problems we used to work on can be reformulated as a optimization problem. So for example, eigenvalue problem. What is eigenvalue problem? Basically, you want to solve eigenvectors which has the following property, right? And that usually requires you to do Gaussian Seidel elimination and a lot of other things, inverting matrix and so forth. But you can also reformulate it as using this Courant-Fisher formula to define lambda as the solution of the following optimization problem. It's just the product of these three terms, okay, with a constraint where the x is a normalized vector. And also solving linear equations, like this is a linear system, and say x is a positive semi-definite, A is a positive semi-definite matrix, then you can solve the linear system by just inverting A and multiply with B. That's what we know in linear algebra. But there are some difficulties in here. Inverting the A matrix can be very expensive if you have a larger linear system. Therefore, this is, even in closed form, it's not very operationalizable, right? And then the variational formulation is like this. Yeah, basically, you're going to solve a quadratic minimization problem. and you can show to yourself that these two things are equivalent. And once you have this, the problem suddenly become different. You can solve a optimization problem by taking gradient descent or constraint gradient methods, which allows you to start from a guess and then incrementally, iteratively drive to equation or to the solution rather than using this approach. Right? So that's basically what the variational methods is generally about. Now let's go back to our graphic model inference problem. I think we said a number of times already, graphic model inference amounts to either computing marginals or computing normalization constant. Sometimes it is also the likelihood. By the way, partition functions, normalization constant, and the likelihood in the world of statistical machine learning often refer to the same thing. Okay. For example, if you have a piece of evidence E, and therefore you want to augment the original distribution E, then what you do is to basically divide them by E, right? And then P of X given E is basically such a renormalized distribution. Therefore, this one is also known as the normalization constant. So we basically kind of compute the likelihood of data in this case. So we're going to see how can we represent these kind of quantities, okay? Z, for example, or P of Xi in a variational form. And one standardized way is to make use of our exponential family distribution representation to give you a universal formula. So this is a expression of the joint distribution in the form of an exponential family distribution, right? It contains a product between the canonical parameters and also the vector of sufficient statistics. Okay, I will give you examples very soon. And then there is a log partition function to make sure that the whole thing normalizes to 1. And there is also, of course, a feasibility space of this formula. For example, the theta has to be such that they are not going to lead to infinity in the normalization constant, right? And every theta that is giving a finite partition function is a feasible theta. Therefore, that's the space of the canonical parameters. And so, for example, our undirect graph model can be also expressed in this way. And Gaussian Markov-Random field is also a member of the exponential family function. And here, the canonical, the sufficient statistic are basically singletons and also, pairwise product of random variables. And their weights are basically the numbers in this inverse of the covariance matrix. We actually knew that already, right? Discrete Markov random field, same thing. You can define indicator functions on X, and then you can introduce singleton weights and pairwise weights. Then your whole thing basically can be expressed by a expression like this: sum of singly weighted potentials and the pairwisely weighted product of singleton potentials. Of course, you can introduce other potential functions if you will. Okay, so these are examples of exponential family distributions. So why this is very interesting? Okay, well, there are some nice properties intrinsic to the exponential family. For example, the mean parameters, okay, can be defined as the expectation of the sufficient statistic. And in the case of exponential family distribution, they often correspond to the marginals of corresponding random variables, in the sense that that gives you a connection to the query that people directly worry about. Here is a singleton mean parameter, pairwise mean parameter. They correspond to the pairwise marginals, given, of course, the canonical parameters already. And then also, the computing of the normalization constant gives you the partition function. There is a good connection in here as well. So how do we compute the mean parameters? Which is actually an inference problem. It basically is like asking how can we compute singleton marginals or other marginals. Well, in the classical approach, that means we need to do summation, do marginalization, right, or expectation. So we have, for example, in the case of a Bernoulli distribution, theta is our canonical parameter. Then we can write down the distribution like this. And the A also can be expressed in a closed form. That's because the whole definition of the distribution is very simple. Then inference, computing the mean parameter, basically is taking the form of a expectation, and therefore summation over all configurations weighted by their probability, right? So this one and this one, and we get this. Okay. So why this is undesirable? Well, because if you have a huge distribution with many random variables, then this expectation step operationally is going to be very expensive. We are hoping that maybe we can solve the mu and maybe even the theta if we get data using a more incremental approach, like a gradient approach. Therefore, we need to have an alternative definition of the problem or expression of the problem so that they become a variational problem. Okay. So how can we get there? For those of you who know the convex optimization literature, you are not going to be unfamiliar with this. We are going to use a technique called conjugate duality. For every function f, you can always define a conjugate dual function, which is the pointwise supremum of a linear function, which is the inner product of a dual pair. In here, the dual pair is the canonical parameter vector and the mean parameter vector minus the original function. So it's the difference between the dual pair and the original function at every point of the theta, right? So geometrically, how it look like? You can view the mu as say a slope of some line. Say this is a slope, a line with a slope mu. Then the differences between this and the function can be always obtained by moving this down to the tangent, of this curve, and then the difference is this much, right? And it's also can be obtained on the axis. And basically, you can define this this is a function for every mu, okay? And the optimizer, theta, can be also in all different places. And this function is called the conjugate dual of the original function. And it is a convex function because you can see already intuitively this is a pointwise supremum of a class of linear functions, like different means and different, it's always like a lower bounding, okay, that original curve, regardless of its convex or not. But this envelope function is a collection of linear functions that is linear. So if our original function f has certain nice properties, such as being convex and being lower semi-continuous, this is a technical condition that usually is satisfied with smooth functions. Then you can then use this conjugate duality again to recover the original function, which is like this. Okay, your dual of dual, okay, is the original function. So now let's assume that our dual function, our function of interest is the log partition function A. Then you can establish the following relationship. Okay, the log partition function now can be defined not as a summation over all the configurations over the distribution, but as a solution to this optimization problem, where you have one term that is the inner product of the dual pair, and the other term is the conjugate of the original function. Now we need to know how this looks like, otherwise we cannot do it, right? Okay, so in this case, the dual parameter mu has this natural interpretation of being the mean parameters in the following sense. So let's see, we are going to now compute, say, just take an example how this all look like under a well-known exponential family distribution, say Bernoulli. Okay, so we know the Bernoulli distribution already, which take the form of this. Remember this form. Okay, the distribution look like this, and also the inference problem gets you the mean in this form. Okay, and the canonical also look like the partition function look like this. So I'm not going to copy it there. So see this term, right? So because A star, which is the conjugate, equals to the sup of the conjugate pair minus the original function. And we already computed the original function in our previous slides. It's basically getting here. And then we need to now solve a stationary condition. You basically take a derivative of this over theta, set them to 0, and you get what is known as the stationary condition. That gives you this expression. Basically, it's also corresponding to mu equals to the gradient of A over theta. And in here, you already can implicitly see, how the mu should behave. They shouldn't be arbitrary mu. There is a range already, okay, defined by how it look like. If the mu can only exist within this range. Okay, what is the range in here? Say if this term becomes arbitrarily large due to some value of theta, then the mu cannot be larger than 1. And this term can be arbitrarily small by some low, very extreme negative value of theta. Then this mu cannot be smaller than 0. Okay, great. Therefore, mu, we could now invert the problem. If mu is outside of this range, then you can kind of guess that this whole thing is unrealizable, right? But if mu is well behaving, then we have all these nice properties. This correspondence between theta and mu is valid. You can actually now infer the theta as a function of mu, and then you can go on and compute basically the conjugate because it is defined as mu and theta and all these other things and get a closed form. So everything is so nice, right? So at the end of the day, we have now an expression of the explicit form of the conjugate. And therefore, the variational form, can be well established. Once your mu is in the right space, that means this mu star, this A star exists. Then you can, you can legitimately define the A as the solution to this optimization problem. Okay, and the optimum is achieved in here as a stationary condition, which actually corresponds to the mean of the Bernoulli distribution. Okay, so this is basically a simple illustration of the whole kind of mechanisms and the tools that you can obtain from this conjugate duality interpretation of variational inference. Now going beyond, let's look at a more generic exponential family distribution, okay, of this form. We still have a canonical parameter, and we have a vector of sufficient statistic, and we have also a potentially intractable, not even expressible, a partition function. We can still write the dual function symbolically like this. And we can still establish the stationary condition of the mu, of the mean parameter, right? And the stationary distribution actually gives you a connection between the mu and the original distribution in the following way. Let's say bring in the A and take a derivative of parameter theta I. You actually get a expectation of the i's sufficient statistic, okay, under the distribution defined by the theta, okay, like this. And this, by definition, corresponds to mu, right? So that's why it's called the mean parameters. This is established naturally, under the expanded family distribution. Okay, so we can now rewrite the stationary distribution like this. So why this is useful? Well, this is useful because you want to use these properties to help you define the space of the mu so that this whole story can hold together. Okay. So now comes to the question. For which mu in the real space, we are going to have a solution for this. Because our goal is to solve this and that, but we need to first define the feasible space. Otherwise, we are going to look for solution, hopefully, maybe in the wrong space. Right? Okay, so now let's look at how the conjugate do look like if such a mu exists. So we have established that mu is under the stationary condition correspond to the expectation of the corresponding sufficient statistic under a given conjugate canonical parameter, right? And then the dual has this following form, right? You can basically bring this into that, and then it gives you the following thing. It's the expectation of this is what expectation of the log of the original distribution. This is basically the entropy of the original distribution. Okay. So after a few steps definition, we know that now the conjugate of the log partition function is actually the entropy of the original distribution when there is a solution of theta, or when the mu is also in the feasible space. Okay. So now let's just review a little bit. There is this nice connection that you start from, say, the mean parameters. If the mean parameters are existent, then you can use the stationary distribution, a stationary condition, to also infer the corresponding canonical parameters. And then once the canonical parameters is existent, you can define the entropy function of the original distribution, and that gives you the conjugate of the log partition function. Okay, and so this symbolically, is pretty straightforward, but solving them, for example, inverting, this relationship, for example, getting theta out of the mu is actually quite non-trivial, and also evaluating the entropy can also be non-trivial. That basically leads to why, inference problem, is complex. In the original setting, we talk about marginalization being difficult, and in here, there are other reflectance of the difficulty, even if you turn the problem into an optimization problem. We saw this difficulty in solving the entropy and in inverting the mu and the theta functions. So now actually it gets a little bit more closer to a theory that can unify a lemma of the approximation technique. Our question now focus on, first of all, finding the domain of mu that such solution exists. That's the first question. Okay, and then once we know this domain, we can see how to approximate the problem of solving, say, expectations of marginals or log partition function, given this domain, in a measurable or explicit approximation way, where either you change the domain, maybe make the domain more easy to deal with, or making the loss function a little bit more easy to deal with. Right. Again, so let's go back to the story. I want to establish a few keywords. One is that we call the domain of the mu, which is defined by the expectation of the sufficient statistic to be called marginal polytope. And you will see in a second why it is known as marginal polytope. And then this is a set, okay, of definition of the marginal polytope, which is basically all the mu's which satisfy this condition. Okay, so this is called marginal polytope, and it is convex. So why it is this? Maybe it's easier to look at it this way. So this integration, if we are taking a discrete distribution, correspond to what? Correspond to sum of xi and of p of xi versus phi of xi, or phi I. Right? And then, by the way, this, I should just put not xi, the x. This is x and the phi I. Okay, and suppose we have, say, suppose that we know this distribution. So this distribution is what? This is basically p of x, right? P of x is basically, satisfying this condition, and also p of x, of course, equals to. So if just we look at this form, this is a convex combination of all the configurations of this phi function, right? And that's our definition of a convex Hall, right? Therefore, this marginal polytope is just the convex Hall of all the extreme points of the sufficient statistic functions. Okay, so that's why it is called the marginal polytope. And maybe I should, okay, this is actually making the definition even more explicit. Right, so here I'm using a discrete case to define that. And that gives you, a more explicit picture about how the convex Hall look like. The extreme points are basically the phi axis with x equals to the configuration. And according to a theorem known as the Minkowski-Weyl theory, you can also, this is how the convex Hall look like. Each of the points basically are the extreme points defined by, instantiations of this phi function in different ways. And then this space can be equally defined by a set of semi-space, such as this one, that one, and that one. So that's basically how this is expressed. Okay. So half space, combinations of half spaces can also help to define a marginal polytope. So before I wrap up, I should give you an example so that we can get a little bit more explicit. Let's just look at a two-node Ising model. Okay, I have a two-node Ising model like this. And my sufficient statistic are three little functions. It's a vector of three items, x1, x2, and x1, x2, right? Singleton potentials and pairwise potentials. And therefore, my corresponding mean parameters are basically the mean of this, the mean of this, and the mean of this. And what does the convex Hall mean? Well, I need to define extreme points. These are the 4 extreme points. Okay, I'm going to basically just plug in x1 and x2 in their all possible value configurations. And that gives me 4 different possible extreme points for this vector. Get it? Right, this one corresponds to x1 equals 0 and x2 equals 0. And this one corresponds to x1, x2 both equal to 1. And this one and 1 and 0. And then these are basically my extreme points. And then the mu space is basically the space of the convex Hall defined by these 4 extreme points. Every mu inside this little shape is going to be leading to a valid theta. And that's basically called a marginal polytope. Okay? So as you can imagine, marginal polytope is a very, very complicated concept. For the 2 nodes, I can write a shape like this. For 3 nodes, you can try. In fact, I would really like you to try it. It gives you 16 constraints. Okay, a lot more constraints. And then if you have more, then writing down the convex Hall or the marginal polytope is going to be impossible. So in our next lecture, I'm going to use about 20 to 30 minutes to explain how are we going to approximate the marginal polytope and also the objective function, like the conjugate of the log partition, so that we can directly solve the optimization problem in a simpler way that leads to the marginals or the likelihood of the data. Okay, but the slides are posted. You can take a look already to get a little bit prepared for next lecture.